So, I'm Peter. My name is Peter Baumann. Thank you for having me here. And okay. So, I'm really grateful and excited to be here. And I also hope that we will get into some discussion after the talk or later in the case. This work that I'm going to present, that is mostly the master thesis of Datacubes, a student of mine. And I want to get you first a little bit away from Python to show you how we came to Python, or which way we took. First of all, a little bit about our fascination. We are computer science guys, you know. So just thinking in terms of bits and bytes, but we have somehow stumbled into the earth sciences and try to share a little bit of our fascination of that topic. Let me show you a little piece that's
planets inside and out. At least that's what we think. After all, we monitor the Earth and its weather patterns from outer space. We measure the Earth's surface and peer into her deepest depths. In today's world of optimal hardware and intelligent software, mankind is reverting to the status of hunter and gatherers. Researchers from all over the world are compiling a vast and very valuable resource, data about our planet Earth. This data affords a new glimpse of our planet. The ongoing exploration of the world has entered the era of big data. But this development also harbors some big problems. Keeping track of the data, making sense of it, is one of the biggest challenges facing mankind today.
So this is the intro to a TV documentary, 1 hour documentary, that has been produced with for German French TV stations. If you go to YouTube, type in Big Earth Data, you can get it in English, German, and French versions. And maybe it's some fun at some time to watch it. Let's come back to this one. So actually, where do we come from? I'm from Datacubes University in Bremen, and let me give me 10 seconds to advertise our data engineering master. By the way, Datacubes University is a fully English place, and we don't need to learn German if you don't want to. So it's an all-English thingy, because we have 100 nations on campus. But 10 seconds are over. Let's come to the topic. So, array databases is the funny thing that we are doing, and that has brought us into Python because we feel, for a reason I'm going to explain later, that this is something very, very important for the users of such technology. And we have actually taken 2 approaches, which I'm going to present in turn. So, let's see. Array databases. Actually, as a computer scientist, I look around and I see data structures. And if I look into all some randomly selected domains here, I actually find a few core data structures, and these happen to be not so many actually. Essentially, what I can see more or less is we need to deal with sets of objects, we need to deal with hierarchies of objects. So this is relational databases, for example, this is XML databases, graph databases, something very, very exciting. Facebook, by the way, has one nice big graph, and try to do graph algorithms on that one. That's an interesting challenge. And then we have arrays. That is something that is ordered in a multidimensional way, and that is what some people like to call a data cube. So programming-wise, it's just a multidimensional array, which can be pretty big. In practice, that turns out to be sensor data, images, so 2D arrays, or image time series, 3-dimensional arrays, simulation output, or statistical data cubes. So that's what you more or less have in terms of applications. Okay, said some people, so let's do database support for that. Classical databases don't do that. And you will see that this is actually a growing wave now, that more and more jump on this. And this has become a quite vivid research area in the field of databases. Why databases? Because they have a classical advantage. They have a query language. So you can send any query anytime and the system will react on it without any administrator holding hands. Maybe for tuning, yes, but not for answering that on principle. This has gone so far that now we are facing a new standard coming up, and that is an extension to ISO SQL to the SQL language with multi-dimensional NDA. You simply get a new attribute type or a new column in your table, so you have something like ID required, some classical columns in a table, and then you have your satellite image in here. So this table can contain lots of scenes with an identifier, each of them being a 5,000 by 5,000 array, for example. This knowledge enables the select clause to do a lot of things for you. You can search and you can process. So you can do something in the where clause, filter, and you can select, and suddenly data and metadata in geoterminology go together and form one uniform information space. So that should make life much easier. And as you see, you can do stuff here, you can retrieve images in different data formats, so we don't need to think in terms of how is that byte encoded and what does the format offer. So that is something that is currently going into the second committee draft, and third quarter of this year, we are going to see the standard finalized as an international standard. That is our hope. Now coming to the strange name here, raster manager. That simply stands for raster data manager, and that is our take on array databases. The idea is simple, the SQL is flexible, and let's just add array support that is missing. So if you will, we have injected an image processing, signal processing, linear algebra language into SQL. That's exactly the standard that you have seen, because actually it's grafted along the concepts of our rasterman system. Okay, so that is the query part, but can this be fast? Underneath, we have put some scalable engine that is based on some principle we call type streaming, and that is running today. That is on OS2 Live, for example, and in operational use, for example, on planetserver.eu. Some people were kind enough to give us some innovation awards for it, so we are listed with CIA review as most promising big data solution. And in the Big Data Challenge of T-Systems at the Copernicus Masters, the Satellite Image Week in Europe, they looked at us, and also the Geospatial World Forum Innovation Award. So, if you want to look at that in more detail, then just direct your browser to rasterman.org, and you will see how to get the source code, how to download, compile it, or get a ready-made VM. And we do some statistics about the downloads, and so you see that daily it's something fluctuating, say on average 10 downloads or so. That's what we are seeing. Okay, so what does that mean? I don't want to go through that in detail. There is a lot of things you can try out. Just to give you a glimpse of it. So if we have some array as an attribute value, we can do subsetting, give me everything in one dimension, do an extraction here, do a slice in a particular position. On the pixels, you can do processing, and for those, for you Python guys, that's no surprise anyway. That looks pretty similar, like what you can do in NumPy, right? You can use it with the where clause if you collapse the array to something that gives you a scalar Boolean value, so you can do aggregates. And all of that is independent from the data format. If you want a particular data format, then say so and do an encoding on the result expression. So that is the idea of the query language. You can do things like visualization. Graphics people told me, did you know, if you take a PNG image and put into the alpha channel not transparency, but elevation information, then WebGL can render this in the browser into something 3D. Cool, we say. That's a query pattern we can accommodate. So we put, say, bands 7, 5, and 0 into red, green, blue. Into alpha, we put an elevation model, we have to scale it to get the same resolution and ship that as PNG. And this is an actual screenshot of an experiment we did with WebGL to render this in the browser. So, eye candy, and I like eye candy. But you also can do more. You can do linear algebra operations, for example, some of those, like you establish a target matrix, and each matrix is the sum of multiplications here. So this is the formula. You can do histograms and a few other stuff. Just to show you a little bit, to give you an impression of what that can do. If you want to try it out yourself, we have a website here that is standards.FOSDEM.com. This is mainly there for advertising OGC standards and showing how they can work in practice. But you can go to a ROSQL console and type in stuff here, like on-the-fly coloring. Then you see the query down there, and then you get a result of some processing on the fly. So that's what the whole thing looks like. Architecture-wise, we have a ROSQL server process that can work on the file system or in a database like PostgreSQL, and that is web accessible. On top of this domain-neutral array language, we have geo-services implementing the OGC standards, and so you can use this as any WCS server, for example. Internally, we do a tiling, a partitioning, of course, and this is something that is a tuning parameter, and you don't see it in the query, but the administrator can determine the tiling and saying, I want, for example, an area of interest tiling, like this one, where I say, these are hotspots, which I want to get the fastest, and everything else, just do something meaningful, say tile size of 1 million cells or so. So that is the storage, and we have databases exceeding 250 terabyte currently. And based on this, we can do parallel distributed processing. So we have a query that addresses different data items that may sit at our server that receives the query. They may sit next to it in the cloud, but they may also sit in another data center. And that is an exciting case in particular, because here you have long distance transport, so you don't want to ship so many data. Therefore, we ship a subquery, and the subquery, the blue one, gets evaluated there, and all that comes back is a result here. In this made-up case, it's just a single scalar that comes back. So this way, we try to have a very efficient distributed federated processing. You even could think of putting up an instance on a satellite, and that's actually something we are really doing. We are really excited that the European Space Agency has selected Rasterman to go on board as an onboard experiment of CubeSat, like this, 3 units, and then we will put this CubeSat into the Federation, and so suddenly the satellite becomes a database server, and a nice gadget for us. Okay, but I hasten to say, yes, we like this language because of its flexibility. But we are very, very aware that this is nothing that users want to see. We do not see this as an end user tool, definitely not, although it's a structured English query language originally. No, we see this as a convenient client-server programming tool. So actually, we want to cover user tools so that users remain in their comfort zone, and their tools stay here in the database. So, JavaScript, if you like that, we have interfaces.
Which for the
and with the help of these standards, these tools all can interface easily to Rasterman without knowing about the internals. So we have a situation, we have a language, but we want to hide it because people want to use something else. And this is where now Python comes in. The first thing I want to present you is OWSLib, OWSLib. Who's familiar with OGC web services? Are there? Okay, a few of you are, others maybe not. OGC, the Open Geospatial Consortium, is a body of around about 500 industry companies, universities, agencies, whatever, that come together to establish and maintain standards in the field of location-based data and services. I'm busy in the field of, guess what, the Datacube stuff. So I'm the editor of the Web Coverage Service Standard. And coverage is, in essence, a Datacube. Okay, OGC Web Services Library is a Python library that allows you to send queries to a server using the OGC standards, but you don't need to build up your request yourself. And that is what has been enhanced by Oliver Fiat from Plymouth Marine Laboratory. He has spiced up the existing WCS support to version 2, the current one. And now you can send WCS requests like getting a Datacube, subsetting a Datacube from within Python. This is pretty much done, so we can demonstrate that. And he's preparing a pull request currently, so that it can become part of the official repository. So that's one thing that can be done. And the second thing that Julia Bargemann has done from European Center for Medium Range Weather Forecast, close to London, she's built a Jupyter which allows you to look at that, learn about it, easily try out. And that looks like the following. If you want to use and by the way, you just go to jupyter.org/GitHub, Earth server-EU, and so on. But you can easily find it via a search engine. So we have some explanations. I establish a web coverage service object, give it the target URL, the version parameter is needed, and then it fetches transparently information about what that one offers. And with Python use, then you go into your contents of the objects and you get all the coverage objects listed by name that you have there. You can access information about a single coverage, and you have a couple of information items which are all defined by the standard, which you can get out there. You can extract them normally via Python means. Very interesting maybe is the bounding boxes. So what is the geographic extent or the spatial temporal extent? And so you get a bounding box and a coordinate system in which these bounding boxes are expressed. And then you can find out, okay, this is a three-dimensional Datacube, longitude, latitude, and time. And here's the detailed information about the spatial temporal extent. You can find out in which formats you can download that. The server may not support all formats. And you can find out at what timestamps we have information available in the queue. So you see, you can drill into the queue and get metadata like here, but you also can access the data themselves. So if you say, I want to get this one. This is the identifier, the CCI, monthly chlorophyll. I want to get it in SCDF, and then I read that file that I get, and I extract information, and with some plotting facilities, I would get out that one in the end. So that is one way of getting data in. But this is getting data. The web coverage service as such allows subsetting, etc., but not so much processing. Okay, we want more. Oops. Okay. Ubuntu says just need to process. But there is no way to escape. Okay, the next thing is, and this is what we are working on currently, is to have a general interface to a database as a backend. And that is actually the MSc thesis now. Take one is, we want to call the rasterman query language from within Python. So we use a communication protocol, we use NumPy for its convenient array handling. And so what you do is you establish a connection to the database, you create a database object, you open a transaction, you send a query, so far so good, but that's not right? You still need to write a string, whereas you would want to program it. And this is actually what we do here. So we use the Python operator overloading to do a lazy evaluation. We collect the operations. We have an A plus B. So we do an overlay of the add magic function.
Sorry.
And suddenly.
So that you're heard at least on streaming.
Okay.
So this is the best we can for this room at this point.
Okay, doc.
Take this somewhere.
Good, thank you. I start speaking. Okay. It's not yet yelling, so I can speak up again. Where we stand now is you still need to establish a collection, and then you say, okay, MR is an object that actually is from a rasterman collection of that same name. This is the information you need to give to Python so that it can do the following. I do my operations as usual in Python. These are not evaluated until you want to get the information. At that time, all these operations are gathered. A string is generated, a query string, which is sent to the server, and with the eval function I get back the array, which I can treat as usual. So actually you don't need to write RaskQL operations like this kind of thing here. You just write your Python code, and then it's translated at runtime into a query. This works for some set of operations, not for all. Okay, iterations, for example, is something we are still wrapping our minds around. What does it say? Oh, not much left. So I should hurry up. So the one thing, the whole activity is embedded into our Earth server project, which is financed by the European Commission, co-funded, and we are very glad about this, where we do analytics on 3-dimensional and 4-dimensional data cubes, where we have exceeded 250 terabytes, and the next is crossing the petabyte limit. NASA Whirlwind is used as a client interface here. And then we have Sentinel images from ESA, ocean color analysis by Plymouth Marine Laboratory, that's the AUSLIB guy, National Computational Infrastructure Australia, and the European Centre for Medium Range Weather Forecast. Those are the guys doing the Python, the Jupyter notebooks. Okay, we've been busy also in open source world for quite some time, and just a little bit about feedback now from my experience is so to say go to meta level. We have gone through 6.5 years of OSGeo incubation, but we are not the longest project. PyWPS has taken longer. So we scratched our head a little bit about the maturity. They are requesting a few things, but for example, there is no document. Of all boats that goes that is something that but the main problem is that actually it's not just about good software, it's something like being intrusive in the project. For example, it favors design by committee over expert leadership. If somebody has a great idea, then this guy should do it. Committee, which may or may not have the expertise in it. Which gets me to something, okay. I hope I'm provocative enough with that. They say all software should be free. I like free software, and I'm very busy in the open source world since 2008. But why does all software have to be free? I mean, projects like the fully commercial thing and the fully open admitted. Okay, sure. Now I get 2 microphones. Very good. What about all these OSG takes care of this one, and none of those ones. Incidentally, you find many SMEs doesn't care if OSG shoots in them. But for smaller companies, they are vulnerable, and therefore actually this policy I find dangerous to smaller companies, smaller enterprises. And that is something I would like to give as a thought to OSGeo. I know that there are some like-minded guys there, but then they are the minority. By the way, the seconds left are also minority, so I should wrap up. We are doing array databases generically. We want to do querying on massive multidimensional arrays. Again, the query language is just some internal interface, and with rasterman community we have some scalable array engine, but we want to hide the query language. Python interface in the world we are dealing with, scientific and technical data, and so we want to establish support for Python as smooth, as non-intrusive as ever possible. You have seen our attempts on that, our way on that. That is still ongoing work, And by the way, let me finish with the idea that we are by far not the first one dealing with multidimensional arrays. As you can see, Salvador Dalí has been thinking about that long before we did. Thank you very much for your attention.